Class is now starting. All attendees are in listen-only mode.
Good morning, everyone, and thank you for joining us for our webinar today. We have Todd from our technical support department presenting today, and he is going to cover inverter sizing. If you have any questions, please feel free to put them in the questions box, and we will answer those as we go along if they pertain to the current subject, or answer them at the end if they do not. Todd?
Hey, Sue, good morning. Did you shift control to me so I can manipulate this? Can you see my screen?
Apologies. Absolutely.
Oh, you're fine. Yeah, let's get that started. Good morning, everybody. While we're waiting on Sue to do that, today's lecture will be two-part, system design, continuing that DIY solar series. This will be on inverter sizing and selection, and then another PowerPoint on wiring and overcurrent protection. So before we get started, though, it was brought to my attention on a previous webinar. Some of the listeners thought I indicated that you should warm your battery bank to like 80, 85 degrees to increase capacity. Warming them to that temperature will, in fact, increase their capacity, but it'll shorten their lifespan. What I was indicating in that prior webinar was how efficient or productive an LED light strip is in actually heating up battery bank when it's cold. Mine was well insulated and in fact got to 80, which took very little power. So that was my point. I didn't mean to indicate that to heat those batteries on purpose. It was a byproduct of just keeping my water lines warm, actually. Okay, this is me. This is my contact information. If you have any questions about this presentation, send me an email at todd@midnightsolar, or just give me a call and we can talk about your system. So in the system design series that we've been doing, we are now at inverter sizing and selection, and have followed with wiring and overcurrent protection. Here's a pre-wired panel, Schneider. This is an E-panel that Midnight makes. This is our classic charge controller. This is an all-in-one package that you can buy. Very nice. Just slap it on the wall. It comes up pre-wired. Again, the basic solar system has solar panels. We call them PV, photovoltaic. A combiner to combine all those parallel circuits into one output, the home run down to the charge controller. You got your inverter, you got your batteries, generator, and your load center. So the basic elements of a solar system. Okay, what is an inverter? An inverter takes DC energy, stored energy, DC, direct current, and it makes as an output alternating current, AC, makes power to power your loads. And you can get two types, two flavors of inverters. You can get a pure sine, which is shown here with a sinusoidal wave, and a modified sine wave, okay, which is square and tops off like that. Modified sine is less expensive on the electronics that produces that. A lot of appliances will accept modified, some will not. We'll talk about that. They come with a cost difference. So those are the two types. So the inverter makes DC to AC, and a converter makes AC to DC. Some of you that might be looking at putting solar in an RV, you'll have what's called a converter. So that's AC to DC. You take your shore power and it'll charge the house battery, plus giving you AC power. Okay. A modified sine wave, like I said, is inexpensive compared to pure sine wave. Usually modified sine waves are found in smaller wattage inverters, like 1,000 watt, 300 watt, 2,000 watt, so forth. Normally in 12 volts or 24. And it's not recommended for delicate electronics. Like this telephone I'm using is actually voice over internet, and I had originally hooked this up to a modified sine, and it was there's a lot of hissing in the background, and so this particular application, my internet telephone, did not like a modified sine wave. It's on pure sine right now. So, and when you get a larger inverter charger, and we'll talk about those to my knowledge are not available in modified. They're all pure sine, which is what you really want. So really try to focus on a pure sine wave. If you're going to live off grid and have a nice solar system, it's well worth the extra money to do that. Here's a couple of examples. This is what a modified sine wave normally looks like. These are smaller inverters, like you might put in a vehicle, a truck, power a stereo, or something like that. This one here actually has an AC block. You can wire this up to a load center. This one in particular is kind of you should really shy away from. I'll show you some numbers. This is a 5,000 watt and 12 volt, and I'll show you the math on that, how much current this thing takes and how big of the wire is. It's really, it should be illegal. It's sinful. Okay, so these are modified sines. That's what they look like. And a pure sine would tend to look more like this. This is a Magnum. This is a Samlex. These are both on our E panels. Midnight makes this back panel. You can see all the AC/DC wiring. We'll talk a little bit about that later on. But the convenience of this, it arrives in a crate. You slap it on the wall. It doesn't get any easier. All right. So if you remember from a previous webinar, we talked about a load analysis. This is actually the very first one. That's the first thing you do, determine your loads. And this is where we came up, we said, if you remember, we needed a 4,500 watt hour was our load, our consumption. That gave us a 9,000 watt hour battery bank. But also a component of this load analysis is to determine the size of our inverter. If we're going to run all these appliances at the exact same time, then we need to have about 2,400 watts of instantaneous power, simultaneous power, right now. I'm consuming 2,400 watts at this very moment. Okay, so that gives us the starting point to determine our inverter sizing. Now, we need to add a little surge. If you have any motors or compressors that you're going to be running off this inverter, you need to factor in their surge. Okay, let's say, for example, you don't. Let's say you take this and you have a 2,400 watt inverter and let's say it has no surge capacity. Most do, and we'll talk about that, but let's just pretend like yours doesn't. So if you have 2,400 watts of all of this stuff running and a motor surges, it's going to push it above 2,400 watts and the inverter will alarm out, shut down. So you need to factor that in. That way a compressor fires up and it's not going to throw your system offline. It's only going to run that surge for like, a second or 2 seconds or so. It kind of depends, but it's a very, very short amount of time. But you do want to factor that in. So when the motor starts on this compressor or a motor, there's a rush of current that's needed to get that motor turning. It's called a surge. So you need to determine all the surge of all the motors, like your freezer, washing machine, refrigerator, and then add that to that load analysis. You can measure it. You can put an amp meter on the power line to that appliance and measure the surge. You'll see it on an amp meter, or you can do a 3 times rule, and you should be pretty close. So if we had a 500 watt motor that runs at 500 watts continuously, its surge would be 1,500 watts. Okay, so 500 times 3. So we have 2,400 watts, and in this example, I'm going to add 1,000 watts for the refrigerator surge. So I would want a 3,400 watt minimum inverter. That's how you do it. So it's kind of a rule of thumb, ballpark. It's not that precise. If you really want to be precise on the inverter, you could do reactive power to the AC appliances. They're not. You don't get a watt for watt. There's a slight loss. It's how efficient or inefficient that appliance is. You could get really into the weeds and the details of sizing the inverter, and some applications are very, very important for that. But a lot of off-grid, SISI, that's not normally done. But you could take this up to a higher level. This, if you added reactive power, let's say you divide that by 0.94, it's going to take it up to maybe whatever the math is, 3,800 watts. If you really wanted to be precise, you can study that online, but it's going to get you in the ballpark. Okay, because your inverter that you're going to get, let's say this is 3,400 watts. Well, they don't make a 3,400 watt inverter. You're going to take that up to 4,000 or 4,400. So because of the marketplace offering that size, 4,400 watts and 48 volts MagnaSine, for example, is going to give you that buffer for the reactive power that you'd factor in there anyway, 99% of the time. Okay, speaking of the Magnum. Now, a lot of inverters will have their characteristics in their part number. So the Magnum is an MS4024PAE. The 40, this represents the wattage. So that means 4,000. This is the voltage, 24. And the PAE means it's a split phase. It produces 240 volts on the output. This is an inverter charger, so it's 4,000 watts and 24 volts, makes split phase 240, and it's an inverter charger. And the charger is, like I said, that converter aspect. It takes AC and makes DC, so it'll charge the batteries. So it's two-way traffic. And in the Magnum in particular has this amount of surge. So I talked earlier about a surge. What will it do? Well, this 4,000 watts will go up to 5,800 for 5 seconds. So it will account for the surge of the motors. So you could factor that in too, that capability to surge it up. So you could buy an inverter that has a good surge capacity, and you don't necessarily have to add it back into your load analysis. You don't have to double add it, if you will. It's a part of this. As you can see here, I mean, it'll surge to 4,800 for 5 minutes. So this is pretty good capacity. So it'll meet most needs. Now we talked about that 5,000 watts. So be real careful. If you're going to start off your system, just really shy away from a 12-volt system. Just realize the low voltage means high current, and especially on an inverter that needs to power a lot of simultaneous loads, it's going to pull a lot of current. So look at this, 5,000 watts. Now here's how you determine the amount of current that the inverter is going to draw. You want to take the low battery cutoff. That particular 5,000 watt inverter has a fixed low battery cutoff of 10.5 volts. It is what it is. It cannot be changed. I think you can hit a dip switch and take it up to 11. But that's still nothing. That's like 10% of your battery. You don't do that. That's one of the negatives about that sort of inverter. You can't take that low battery up higher. If you allow that thing to shut off on its own at 11 or 10.5, you're going to be beating up your batteries. It's just not good. But you have to factor that in. So let's go with worst case. So 5,000 watts divided by 10.5 divided by the efficiency factor, meaning it's 15% loss, 85% efficient. That gives us 560 amps. That is an incredible amount of current. You'd actually have to use like 2 4-aught cables for the positive line, 2 4-aught cables for the negative line, running it to a 560 amp fuse, because they don't make a breaker that big. Well, we don't. This is our largest one, 250 amps. You can see it's 7 inches in length at 250. We don't make one that big. So if you're going to run a sizable system in 12 volts, I wouldn't go more than like 2,000 watts in 12 volts. And, you know, if you have even a small cabin off grid, you're going to be beyond that. Go 24 at least. You'll be happy with that. And this is why. You just don't want to be playing with this amount of current. Okay. Okay, so we talked about the inverter. Inverter takes DC and makes AC, but the charger side of this is very, very important for off-grid living. The charger will take AC from either the grid, or if you're off-grid, from your generator. And it will use it to charge the battery bank, and excess capacity will be sent downstream to the load panel to power your loads. So an inverter charger is going to be more expensive than just an inverter, but when you're living off-grid, it's worth it. You know, the winter days, you're just not getting enough sunshine, sunlight intensity, you're not flowing any energy from the PV. You're going to have to fire up the generator, which means using the charger. So plan ahead. It's well worth the extra expense to get that. So again, this is a pre-wired system here. This is the Magnum pure sine wave. This is either 4,000 watt and 24 volts, or 4,400 watt and 48. They look the same. And this is all the wiring inside. These are our surge protectors for near lightning strike. Classic charge controller. This is the Magnum's control panel. That's how you program it. And all this wiring. So this is all the inverter side of the system. It all comes together right there. And this is what it looks like electrically inside that box. This is what you're getting with that pre-wired. Now you can buy that box and build it yourself, wire it yourself, save a bunch of money. But if you don't have that enclosure housing these wires, all this stuff is going to be mounted on a piece of plywood in your solar room, in the shop or the garage or wherever your batteries are. Batteries will usually be around here. You're not supposed to be below it, but they'll be situated here. So these wires that are running down to the battery, 6 to 8 feet. So the battery, this is your battery room. Your inverter is going to be in there. So it just makes it easier. So this is all the AC wiring. Okay, this is the inverter right here. This is what you get with that box. And here's the DC side of this, the charge controller going up to the inverter, down to the batteries. So all this wiring right in here is included in that box. So it just makes it so much easier. Okay, so when you're sizing your system, we were looking at the load analysis, your instantaneous power we threw on the surge. So the instantaneous was like 2,400 watts. We added 1,000 watts. So we said we need a minimum of a 3,400 watt inverter. So for the most part, that's how you size your inverter. You chase, let's say, a 4,400 watt inverter and 48 volts to meet my load analysis. And it comes with, let's say, a 100 amp charge controller or a charger. So you don't really necessarily, for the most part, you're not chasing the charger side of this. As when you're sizing an inverter, you're sizing it on the inverter side. Okay, I'm just kind of pointing that out. Now, if you are running your charger, let's say you're running at 100 amps, for example, and you're getting some solar through the Classic to the batteries, so you got 100 amps for the charger, plus you got what the charge controller of the Classic is doing. You got to be mindful that you're not exceeding the charging limits of your batteries. So just at that moment in time, be mindful of that. So that's pretty much it on the inverter sizing. Are there any questions, Sue?
Nope, none that I see yet.
Okay. I'm going to take this down, and we're just going to roll right into the next, the wiring. Okay. So this is the last in the DIY series, wiring and overcurrent protection. Again, our basic solar system. Okay. So wiring, the wire needs to carry a certain amount of current. Overcurrent protection protects the wire from failure. Okay, that's basic concept. Size the wire to carry the current and size the breaker to protect the wire. That's what we're going to talk about. So current is 1 ampere at is 6.28 times 10 to the 18 electrons per second. That's a lot of electrons. Okay, that's a billion times a billion. And an amp, it means the rate of current flow, because it's per second. So when we're talking like 40 amps, it's 40 times this number. That's actually the number of physical electrons that are traveling. They're agitated, they're excited, and they're traveling down the wire, and it creates friction. And if the wire is not large enough to accommodate, let's say 40 amps, again, 40 times this, truckload of electrons, it's going to create heat. And that heat is what's going to build up, and it's going to break down the insulation on the outside of the wire, and it gets to the point where that cracks and breaks, and you get a fire. And that's why you want that breaker to step in there and interrupt that, break the circuit, disconnect, to stop that accelerating heat. So a larger wire, meaning larger in size, bigger in physical size, means more copper, means more easier free electron movement, means less resistance. The smaller the wire versus that same amount of current is more resistance. More resistance is heat, too much equals fire. So that's what's to be avoided. So this whole concept is safely, properly sizing your wire to carry the amount of current. So you never have this buildup of heat. You never have a problem. The problem is if you don't understand how to size it, or you're trying to save money by buying the next smaller size because it's copper. Copper is expensive. This is what it will lead to. This is the end of the road, is fire. That's bad. Okay, so we talk about wire and gauges. It's the we call it AUG. Like a 10 AUG means AWG, American Wire Gauge. Now, one thing you got to learn is the smaller the number, the larger the wire. So here, 12 gauge is actually, the wire itself is actually smaller in physical size than a 10 gauge. A 22 is like a really, really small little wire compared to a 10 gauge. Okay, so those are inverse. So just learn that, get a little chart like that. Here's an amp chart that I tend to use quite a bit. It'll show the approximate allowable amps per wire gauge. Okay. Now there's different ways you can read this chart. I use this as a ready reference. It's not the one and only. And there's others that go up to, that show more precisely actually what this is actually a very conservative chart. It's like 4 gauge. Here we go up to 130 amps free air. So I use this. Okay. Another concept in determining your wiring, especially between the panels and the charge controller, is what we call voltage drop. Voltage drop is just caused by resistance. Okay, Ohm's law. So if your panels have a voltage out here of 112 and you're running all those electrons through a wire that's a little too small, it creates the resistance, slows it down. It effectively drops the voltage by the time it gets over here. What you'd like to strive for is this proper size wire that allows no more than a 2% drop. So between this point and this point, if you can keep it at 2%, that's great. That's more power for you. If you drop this voltage, you're losing power. It's robbing you of power. The Classic can only process what it's being presented. So more drop equals less power. So if I drop the voltage and the current stays the same. Remember, that current's going to try to run through there. Let's say it's 10 amps. It's going to run through there regardless. It's just going to squeeze through that bottleneck, i.e. the smaller wire, and it's going to create heat. It's just not very efficient. But you're going to, the voltage is now dropping, so the wattage will drop. The wattage that the Classic will make will drop. So that could be an expensive wire, that home run. That represents all of your panels in parallel, numbers might call for a 2-aught cable. You try to get by with a number 2, you're going to pay for it with a voltage drop. So that's what it's all about. Okay, some factors from the National Electrical Code that impact wiring size. There's a bunch of them. We're going to talk about 2. The anticipated current draw of the load, continuous duty, or 3 or more hours, and there's other factors that you can derate wire, and we'll talk about that in a second. The temperature, if the conduit is exposed to sunlight, the type of insulator, how many wires are in the conduit, and ambient temperature up on the roof. So there's a lot of factors. This presentation, I'm just going to present these 2 because we can get into some great detail about this. This here is, you'd have to study, like I said, the NEC, speak to an electrician, or study this on your own. It can get really in depth. So we'll talk about these 2 here. Okay, this is the first example. We're going to size the wire between solar panels and the charge controller. The characteristic you need to take a look at on the back of the panel is a short circuit current, 9.12 amps for this panel. Now, in this example, I'm just going to pretend like it's a single panel between the PV array and the charge controller. So we have a short circuit current of 9.1 amps, and we have a distance from the PV array to the charge controller of 45 feet. So there's going to be 2 calculations that we do to determine the size of the wire. The first one is we're going to increase, we're going to take the short circuit of 9.1 and we're going to increase it by a factor of 1.25 to say that the max current potential is 11.4. Panel gets cold, hit with a higher intensity than the standard test conditions. This panel could actually make more current than it's rated. So we're giving a little buffer to say, hey, the max that it could pass is 11.4. Now we need to size the wire that can safely handle 11.4. Okay, so the second rating here is for continuous duty. Now the concept is that I can't push that wire to its max. I need to derate it. I need to say if I got 11.4 amps, I can only push 80% of that through a certain size wire for 3 hours or more as a safety buffer. Nobody's going to downgrade their current. So what they do is they do the inverse. They up the size of the wire. So 1 divided by 0.8, 80%, is 1.25, hence this 1.25. So we're going to increase the size of the wire, which is the same concept. If I have so I'm going to say 11.4 times the second multiplication of 1.25 gives me 14.2. If I take 80% of that, it gets me back here. So it's the same concept, it's just the inverse. So on the PV wire, there's 2 multiplication factors. Each one is 1.25. The first one tells me my max current. The second one gives me the ampacity of the wire to safely carry a continuous amount of current for 3 or more hours. So this is my final number, 14.2. Then I can look on that sizing chart like I just showed you a while ago. What size wire will safely carry 14.2 for 45 feet? And it's real close. It's 6 or 8 gauge. It's kind of right on the line there. So that's how you do it. And then, okay, so the 15... So the 8 gauge right here was actually to 40 feet, and I said an 8 or a 6. Yeah, most people will probably do an 8 in that example. Okay, so to explain this again, just so you understand, we're starting with a solar panel of a short circuit current of 9.1. And the 9.1 needs to be elevated because in a real world, the panel can produce more. So the first safety factor, I'm upping it by 125%. Gives me to 11.4. So this 9.1 amp panel can, at times, not always, but at times, could theoretically make 11.4. And that's the amount of current I need to safely push through a wire. So the next factor is what size I need to up the wire to safely carry 11.4. So a wire that can safely handle 14.2 can safely carry 11.4 continuously. That's the concept. So I'm starting with 9.1, and I multiply it by 1.25 to get here, and I multiply it again to get to here. Now, a lot of people will skip a step and just multiply it by 1.56. You might have seen that before. That is actually 1.25 times 1.25. They're just skipping a step and jumping ahead. So you start with 9.1, multiply it by 1.56, and you get right to this answer for the ampacity of the wire. Okay, so I just wanted to explain that. It's not very crystal clear, especially if you read one of the NEC books. It's actually more confusing than when you started. So I just wanted to clarify that. Now, onto the breakers. Midnight breakers can carry 100% of the current. Now, remember in the previous example of the PV, we had we needed to push 11.4, but the wire cannot carry that continuously for 3 hours, so I up the size of the wire. Well, we don't do that with the breaker. The breaker can carry 100% of its rated current. You don't have to up it. You don't have to derate it by the 80% or the inverse, increasing it by 1.25. It's not necessary. So in this example, we're starting with a short circuit current of 9.1, and we're saying that the max possible PV current is 11.4, which is that first 1.25. Then we take it to the 14.2 for the wire ampacity. But in this application, the max current is 11.4. If I got a 12 amp breaker, it can carry 100% of the current forever. So I can push 11.4 amps safely through a 12 amp breaker. I don't have to up the breaker at all. Okay. Now, if you're using a non-midnight breaker, you have to do this second derating because it cannot carry 100% for more than 3 hours. So you have to derate it by the same concept. Make the current flow 80% or 20 less, 80%, or up the wire or the breaker size by 1.25. And it's all down in here. So if you use a midnight breaker, it's based upon this first 1.25. Now, I will say in most applications, you're not going to put a 12 amp there. Just in practical terms, it's just not. You're going to go with a 15 amp. It's just the way it is. So, okay, now sizing the inverter. We had an example earlier. Well, we'll continue with that. Let's say we have a 4400 watt inverter, and the low battery cutoff is programmable at 46 volts. 46 volts on a 48 volt system is 10%. I hope you don't actually have your low battery cutoff that low. You really should have it at the 50% level, which is 48.4, maybe 48.5 on sealed batteries. But because the inverter could operate down at that, it's best to size it based upon the worst case scenario. So you can find out what is the low DC disconnect on the inverter at which it shuts down. I think I took this out of Magnum's book. I think it will actually shut itself off at 46. So that's what I'm going to use. And the Magnum is 93% efficient, so I'm using those their exact numbers. So this inverter running at full steam at a low battery voltage of 46.3, having a little loss on its conversion from DC to AC, it's going to pull 102 amps at this moment in time. So that's my starting point. That's where I want to start my wire sizing based upon carrying that. Now, the inverter can surge to 5800. That doesn't mean you're going to do it, but you never know, what may happen to your inverter. You're not there. Somebody may fire it all up. So you want to surge it, again, 135. Now, this could be continuous through that wire, so it's the same concept. If I'm going to push 135 amps through my wire for 3 hours, which you're probably not going to at a battery voltage of 46 volts, you're at 10%, it's going to wear itself out. But let's just say you had a big battery bank. You need to up the size of that wire as well, so it's the same concept. So I'm going to multiply that by 1.25, so 168 amp sized wire will safely carry 135 amps for 3 hours or more. It's the same concept, okay? So then I would look on the chart, and a 2-aught, this is called 2-aught, it's larger, is good for up to 200 amps, and I'll put a 175 amp breaker on it. And then I've got this this inverter covered. And that would be between the inverter and the battery bank. That's how you size that. Okay, just as a review, I've got from the panels to the charge controller, I'm going to determine what is my max current, which is a multiplication factor of 1.25, and then what size wire can carry that max current continuously, my second 1.25. On the charge controller, I don't determine max current because it's current limited. it can only produce X amount of current. Let's say the Classic 150 and 12 volts, it will only ever make 96 amps on the output. So I'm not going to increase it by 96 times 1.25 because it will never go above 96, so it's current limited. Now, I will say what size wire can safely carry 96 amps continuously for 3 hours or more, and that is an ampacity calculation of 1.25 for the wire between the Classic and the battery bank. The inverter, its max current is determined by the low battery cutoff. Remember the example, 5,000 watts divided by 46 volts divided by efficiency gives me whatever, 140 amps. So my maximum current is that moment in time right before the inverter shuts off because it's at low voltage. Remember, when voltage goes down, current goes up. And I will multiply that wire, that max current derived by that low battery cutoff by 1.25 to determine what size wire can safely carry 80% of the current. It's the same concept. Okay. All right, now we're going to get into some circuit breakers. We have two types of circuit breakers. These are called DIN rail. You can see right here, this mounts on a little metal sleeve, and it's held in place by this little tab. You just push it up, and the circuit breaker's on the front. This is the little channel that the wire goes into. There's a Phillips screw head here. You tighten it, and this little saddle will tighten up on your wire. Now, this particular DIN rail mount is polarity sensitive. You'll see that this is marked on the bottom plus plus. On the top of some of them, it's marked minus minus. Now, don't be confused on this thinking that the positive goes in the bottom and your negative goes in the top. If it's marked negative up here, it's the lesser of the positive side. You're only going to put circuit breaker on the positive wire anyway. So the positive comes in the bottom and positive goes out the top. But this is polarity sensitive in the way this mechanism captures the DC arc when it's tripped or when you turn it on or off. So this negative up here means the lesser of the positive side. This points towards the highest current source, like I have right here. So in this application, and I'll show you an example, this would be the wire that goes to the solar panels, you know, way out there to the left. Or this is the wire that goes down to the battery bank, down here. Oops. So our breakers, this DIN rail by itself is rated 125 volts DC. And if it's in one of our midnight enclosures, like a baby box or one of our E-panels, it's listed at 150 volts. Okay. And just remember, the circuit breaker protects the wire, not the equipment. By protecting the wire, secondarily, it protects the equipment. But its actual job is to protect the wire so you don't have that heat buildup and that breakdown of the insulation, which usually always makes a fire. This is a panel mount. It means it's mounted on the face, though that screw right there and there is what secures it in place. It has studs on the back, which accept what's called a terminal lug. So you'll run your wire in here and crimp it, and you need to put some heat shrink on there. You can see this heat shrink reduces down and it makes a nice seal. There's some glue or something inside there that oozes out and makes it waterproof. These here are non-polarity sensitive. It's not, the positive and negative is not, you don't have to be mindful of that. The current can flow either way. It can capture the DC arc. It does not have the same internal mechanisms as the other breaker does. And this is rated at 150 volts. We do have some 300 volt ones. If you have a higher voltage input between the PV and the charge controller, you put a bunch of panels in series, we do have up to 300 volts. All right, so breaker sizing. Okay, let's say you have a 4 gauge wire, 4-AUG or 4 gauge, and it's good for 100 amps. You want to put a breaker on it that's rated up to 100 amps or less. Don't put, let's say, a 150 amp breaker on 4 gauge wire because the breaker is not going to trip until it sees 150 amps. 150 amps exceeds the limit of the wire. May or may not burn it up. You don't do that. Okay, so here's an example. Let's say a Classic 250 48 volt battery bank and its max current out is 55 amps. We'd recommend using a 6 gauge wire, and 6 gauge is good up to 80 amps. So you can select a breaker between 55, well, we don't make that, but let's say 60 amp to 80 is good. So if you selected a breaker larger than the wire's ampacity, 6 gauge is good for 80. Let's say you put a 90 amp breaker on there. Again, it's not going to trip until the wire starts breaking down, and that's a safety factor. If you went below the 55, then it's going to get nuisance tripping. If that Classic is pushing out max current, you got a 40 amp breaker on there, it's going to be popping all the time. So there's where you size your breaker. Is anywhere along here will protect this wire. Okay, that's how you do it. All right, now I'm going to show you kind of putting this all together. This is a basic diagram. We show our charge controller here, our battery connection. Remember I said the breaker goes on the positive leg, negative just goes down to the battery. Our solar panels are coming through a combiner, and the positive flows to this breaker. And I'm not going to talk about this one here. I didn't have a simpler picture to put on here. I looked, we just didn't have one. Okay, so this is the combiner box. This is what a combiner looks like. Just pay attention to this one over here. These are circuit breakers. So we're pretending like I have 3 parallel strings coming in, and the positive of each string of panels, remember a string is a series, a row of panels, positive to negative, positive to negative. Okay, the end of that string, on one end will have a master positive and the other end will have a master negative. The positive will go through the bottom of this breaker, and its negative will land on this bus bar. Let's say we had 3 strings. So you're going to have 3 positives coming in here. And now this bus bar is combining the output. It parallels it, puts it all together. And this is your home run that we would size. So this is what's coming from here to the charge controller. So in this example, and I'm just going to speak to this out loud, let's say we had that 9 amp panel, and I had 3 of them. This 9 times 3 is 27 amps. So the minimum here is 27, but I need to up it for max current. So it's 27 amps times 1.25. And without getting out the calculator, let's just say that's 35 amps, for example. Then I'm saying, okay, 35 amps is going to flow from this lug bolt right here, this red line. 35 amps is going to flow here continuously, more than 3 hours. So I need to determine the ampacity of the wire. So that's that 35 amps now times the second 1.25, and let's just say that's 50 amps, for example. So then I decide, okay, this wire needs to carry 50 amps over this distance. Let's say it's 50 feet. 50 amps for 50 feet. Then I look at that amp chart, and then what size wire can carry 50 amps for 50 feet? That's the size of my positive and negative home runs from the combiner to my charge controller. That's how you do it. All right. Yeah, I spoke to that one. I had the picture right here for you. Okay, so again, the 9.1, we got 2 strings. It's exactly what I just said. Oftentimes you use 10-gauge wire between the panels and the combiner, and oftentimes you'll use the 15 amp breakers. Now, you do want to be mindful of this one thing here. Look on the back of the panel. It says Max Series Fuse Rating. So if you remember back to the previous, I did 9.1 times 1.25. Max current was like 11.5 amps. And if you're using a midnight, that's it. You reference off of that. So I could have run a 12 amp breaker. And like I said, it usually is up to 15 because 12 is a little close. But I don't want to do a 20. Even though I'm using 10-gauge wire from the panels to the combiner, 10-gauge carries 30 amps. Technically, if you remember back to the previous example, I said your breaker can go up to the max ampacity of the wire. Well, you're using a 10-gauge because that's very common. It does 30 amps. But in this example, you're limiting your fuse to what the panel wants, the panel manufacturer. So it'd be a 12 to 15 amp, hence 15. So sometimes you'll see this at 20 amps. But again, you're not going to go up to the full 30 amps because you're running on a 10-gauge wire. So this is a limiting factor, and you do want to be mindful of that. Most always it's 15 to 20 amps. I just wanted to point that out. Now the charge controller sizing, we have this in the classic manual, and this is already calculating and figuring in a multiplication factor for ampacity. So I pointed that out earlier. Let's say a classic 150, 12 volts makes 96 amps. You take 96 times 1.25 and come up with the number, whatever it is. It's like 120 some amps. Well, number 4 gauge is actually in open air will allow that. So you can just go off this ready reference here. You don't have to do the math on that. Classic 150, number 4 gauge, 200 and 250, number 6. In open air environment, it's perfectly sized. So that's that. And that concludes the wiring and overcurrent protection webinar. This is the last of the series. Sue, do we have any questions?
No questions yet. I want to thank everybody for joining us today. And please remember that we have another webinar featuring Ryan from our technical support department on Thursday. And that will be on DC power systems as an overview. It'll show a lot of the common issues that we see in tech support and a lot of interesting stories. So we hope all of you can join us for that. Looks like we have no questions, so we'll go ahead and wrap it up. Thanks for doing that, Todd.
Thank you very much. Have a good day, you guys. Be safe out there.